Now let us see design and test bench code for 1-bit comparator and 2-bit comparator, and we have seen its hardware implementations. Now let us try to generate Verilog code based on that hardware implementation. As we know, every Verilog code starts with module and ends with end module. So I am starting with module and I am providing a name. What are the outputs? GT, EQ, LT. What are the inputs? A, comma B. Here we need to declare input A, comma B, and we need to declare outputs, that is GT, EQ, LT. Sorry, GT it is. And then first let us write equations. What is GT? A, B bar. What is EQ? A, X nor B. What is LT? A bar B. Now, before writing Verilog code for this, we don't know what is B bar. Here, what is B bar and what is A bar. So, we will take wires. So, wire A bar, comma B bar. Now, what? How to get A bar and how to get B bar? So, we use not get for that. What is the output? We need to get A bar, comma A. What is the input for not get is A. And to get B bar, we need to use another not gate. So B bar, comma B. Now the main outputs GT, EQ, LT. How to get them? Uh, GT is what? A into B bar. So ungate. First outputs we need to write A, comma B bar, and LT. LT is the output. What are the inputs? A bar, comma B. EQ. Sorry. To get EQ, what is the gate? XNOR G5. Those are inbuilt gates. You no need to worry about them. How it functions. EQ, comma A, comma B. That's it, our design code and module. We can even write assign statements like assign A bar equal to not of A. Like this also we can write for everything. Suppose for this, assign GT equal to A and B bar. Now let us write test bench code for this. No, we will generate one file for comparator 1bit.sv. Comparator 1bit tb.sv. Module tb, reg input as regs, right? Reg a comma b, output as wires, wire gt, eq, lt. These internal wires we no need to declare in test benches. Okay, just main inputs, main outputs we are declaring. Now this is common procedure. 1-bit dut instantiation. GT, comma EQ, comma LT, comma A, comma B. We have written port by order. How to write port by name? I think I have already discussed about this. Okay, once again we will see. I'm not writing in order now. See, first I'm writing a dot a of a, comma. Now I am writing gt. But when we write port by name, it doesn't require any order. We don't want to write the same order. If we write in the same order also, no problem. If it doesn't write in the same order also, this simulator won't give any error. Okay, then initial, begin, and then I want to see for 5 iterations. Now we will try to use for loop. Till now we have discussed about dollar randoms, repeat 5, right? Now how to write for loop? Let us see. For I equal to 0, I less than or equal to 5. 5 I will give. I equal to I plus 1. Before declaring what is I, before writing what is I, we need to declare what is I. In C or C++, we declare it as int. Here in Verilog, we need to declare it as integer I. Begin the same procedure like what we used for repeat 5. The same a comma b equal to dollar random. Here in place of repeat 5, I have written like this. Okay. Hash 1 dollar display. We need to print the results, right? So dollar display a equal to percentage b, comma b equal to percentage b, comma gt equal to percentage b, comma eq equal to percentage b, comma lt equal to percentage b. A comma b comma gt comma eq comma lt. That's it. And then we will end with end keyword. Yeah, this is our test bench code. So we have generated here separate files, right? So we need to declare it here by using tick include. Both design and test bench we will include here only. 1 bit dot sv. Tick include comparator 1 bit tb dot sv. The same names we are writing here. Now let us try to run. Before running, we need to select a simulator. And now, after running, this is the output we got. If A equal to 0, B equal to 0, GT equal to 0, whereas EQ equal to 1. EQ became 1 because A equal to 0 and B equal to 0. That is, both are equal. When A equal to 1, B equal to 0, GT became 1 because A greater than B. So that's it about 1 bit comparator. Now let us see for 2-bit comparator. I am generating another file here, comparator 2-bit dot sv, or you can give v dot v. The same follows here. Module. What are the outputs? The same gteqlt comma inputs. But here inputs are 2-bit. not 1 bit, right? So we need to declare like 1 down to 0, a comma b. Outputs are 1 bit. Now if you look our hardware implementation, we have used two 1 bit comparators and 3 bit wide multiplexers, right? So before writing this Verilog code, let us write 3 bit wide mux 3 bit wide dot sv module mux input. What are the inputs? Select line I1 I0. So s comma I1 comma I0 or inputs. What are the outputs? Just oh no, and also here S is only 1 bit, whereas I1 and I0 are 3 bits. So input, because it is 3 bit wide mux, so input 2 down to 0. Output is also 3 bit wide, so output 2 down to 0 by, and with braces and also semicolon. Now assign y equal to s ternary operator. If s is true, you give I1 as output, otherwise give I0 as output. End module. That's it, our 3 bit wide mux. Suppose s equal to 1 and I1 equal to 001 and I0 equal to 100, then y becomes, what y will become? 001, because when s equal to 1 here, so s is true, it will give I1 as output. When s is false, it will give I0 as output. In the same case, when s equal to 0, output y becomes 100. So this is the functionality of 3 bit wide mux. Now 3 bit wide mux we need, and also 1 bit comparator we need. Let us include those two files here. How to include? By using tick include comp1 bit dot sv, and also tick include mux 3 bit wide dot sv. That's it, we included both files here. We can even write this whole code here, but why I'm not writing means it becomes some clumsy and we confuse a lot, so that's why I included like this, so that by looking at this line you can think like, okay, comp1 bit.sv we have included, so let us go to comp1.sv, like that. So we can think in that way. For documentation purpose, I have written like this. Now coming to here, comp1 comp1, this name we need to write. Comp1 bit we have given, so some a1 or a0 instance name is doesn't matter. We assumed in our hardware implementation g1 comma e1 comma l1 as outputs, right? And what are the inputs? A of 1 comma b of 1 for one comparator, and comp 1 bit a2 g0 comma e0 comma l0 comma a of 0 comma b of 0. Next, we used mux, two muxes in our hardware implementation. So mux 3-bit wide. If you look at our hardware implementation, we have used two muxes. So according to that, I'm going to write Verilog code now. First mux, here we already implemented the Verilog code for mux 3-bit wide. So that we are instantiating here. So mux A3. What will be the output? The main output, that is GT, comma EQ, comma LT, comma, why I have written flower braces? GT, EQ, LT are 1 bit wide. If you write it in flower braces, then if output is 1 comma 1 comma 1 comma 0 comma 0, then it will show as 1 0 0, and also our output here is 3 bit wide, right? So that's why I have written GT, comma EQ, comma LT in flower braces. Actually, here what order we followed? S first, I1 next, I0 afterwards, and then last Y. So we need to give here output at last. So let me do like this. Sorry. Yeah. First, what S? What is select line here? G1, and then one of the input I1. That means 100. So for that we need to write 3 tick b 100, comma, what will be the another input? Another input is output of another multiplexer. So let us assume it as wire, we will say like y0, and then output. Now another multiplexer, mux a4. What is the select line for this multiplexer is L1. I1, what will be the I1 here? 001. So 3 tick B 001, comma. Oh, this is not I. Sorry, L1, right? Okay. And then what is another input? Another input is the output, the three outputs of comparator, which gives output as G0, E0, L0. Since it is a 3-bit wide, I am combining them and I am introducing them in flower braces. G0, E0, comma L0. And what is the output here? Y0. So that's why I have written Y0. Now we need to declare Y, because simulator doesn't know what is wire. Y. Wire, how many bit wide? Why not 2 down to 0, since it is a 3-bit wide. Why not? Right? That's it. We have obtained our main outputs here. If you look here, yeah, we will write n module. This is our 2-bit comparator design code. Let us go to test bench. The same test bench we will apply, but we need to do some modifications. Come 2-bit tb.sv, create file. Same I pasted here, but here what input is 2-bit wide, so I'm changing that. And also they are written caps, right? 0 a comma b.
The same thing here also we need to write. Otherwise, here in design they are written in caps. Let us write here in small letters, and then we will here what it means dot a, dot a capital A in design code is replaced with small a in test bench. That is what it mean. Okay, here also remaining whole is same. Yes. Oh yeah, this I need to change to comp2, not bit also. We have written here comp2, just comp2. So I have written like this. That's it. This and all I am not changing capital A because here we used small a and we said like please connect with capital A. By writing this, here small a will connect with capital A. So this is our test bench, and before we have included one bit, so let us comment this, and then we will include 2-bit comparator files. Tick include comp 2-bit .sv, and then tick include comp 2-bit tb.sv. That's it, right? Now let us try to run it. See here, when a equal to 1 0, b equal to 0 1, gt became 1. Why? A equal to 1 0. 1 0 in binary is equal to 2 in decimal, whereas b equal to 0 1. 0 1 in binary is equal to 1 in decimal. Always 2 is greater than 1. So that's why, that means a is greater than b. That's why gt became 1 here. And also a equal to this also gt equal to 1 only, right? Okay, we will see this condition. A equal to 0 0, b equal to 1 1, b equal to 1 1 in binary is equal to 3 in decimal. So always 0 is less than 3, that means a less than b, so lt became 1 here. Here I think we gave random, so it doesn't take two equal numbers. So let us try to give two equal numbers for a and b. Okay, sorry, comp 2-bit tb. Yeah, here only we will change. Okay, here we assumed a as 2-bit. Let us write a equal to 3, b equal to 3. We can give in decimal, it won't show any error. See the last one, a equal to 3, b equal to 3. 1 1 in binary is equal to 3 in decimal. So that's why EQ became 1 here, because both are equal. Let us try to give 4 and then we will run it. We will give here percentage d because for our understanding we can easily understand the decimal numbers when compared to binary, right? So
We have given a equal to 3 and b equal to 4, but what it is printed here, a equal to 3, b equal to 0, and it shown here as gt is 1. That means a is greater than b. But what actually it should print is a is less than b and lt should be 1. But why it didn't print lt as 1? Why it printed b as 0? Why it took in this way? Because b equal to 4 in binary. What 4 in binary is 100, but b we have taken only 2 bits. So that's why the simulator assumed and have taken the last 2 bits only. It doesn't take the third bit because b limit is up to only 2 bits. So that's why it have taken 00. 00 in decimal is also 0. So that's why it printed b as 0, and it have shown result as gt equal to 1. So we need to look carefully what we are giving and what we have written here. Okay, let us keep b equal to 3 only here. Now see, a equal to 3, b equal to 3, both are equal. So eq as 1, lt equal to 0. So that's it guys. If you have any queries, let me know in the comment section. Stay tuned for more videos. Thank you. Bye.